today. So I'm going to be talking about the physics of collider physics, and this is very high energy collisions of protons. And really what I want to talk to you about is what are the kind of mathematical tools, how do we make predictions for what we see when we make these very high energy collisions? And that's this notion of factorization. And what the factorization will give us is products in some space of what I call these universal functions. So that's the subject of my talk. So I'll start out with a fairly general introduction to the physics of colliders, and in particular also talking about the strong force, which is the most important force in describing these types of collisions. And that will lead up to our discussion of the discovery of the Higgs boson and kind of the things that go into that discovery. So that'll set the stage for my talk. And then we'll talk about what this factorization is, how it comes into predicting things about the Higgs boson, and how we can use quantum field theories known as effective field theories to make those predictions. And I'll give you some examples, and then if there's time, I'll talk also about factorization violation. Okay, so let's start very generally. Let's take a one-dimensional view of physics. So we can take a one-dimensional view of physics if we put everything on one dimension, which here is distance. And so we have large scales, the scale of the galaxies, all the way down to these small scales involving the size of protons and the wavelengths associated to protons and electrons, and kind of the energy frontier here, which is this TeV scale. So very high energy probes very short distance. This is the Broglie relation. Energy and wavelength are inversely related. And the standard model of particle physics is kind of what you think of as the underlying theory for describing a wide range of possibilities here. But there's kind of endpoints where, for example, we don't have a dark matter particle in the standard model, which is needed for galaxy formation, for example. And also on this other endpoint, which is where I'll be talking today, we have things like new particles that we can discover. Higgs boson is part of the standard model, and I'll be talking about that. But you might wonder what's over here. That's this question mark, and that's kind of interesting physics that we're trying to probe with these colliders. So the TeV scale is kind of where most of my talk will take place. Okay, so what is the standard model? We have four fundamental forces. Most of my talk will be about the electromagnetic strong and weak force, and indeed most, as I've already said, will be about the strong force. The electromagnetic force is intuitive to everybody. The gravitational force is intuitive to everyday experience. So what's the strong force? The strong force is the force that binds together quarks and gluons into a proton. And I'll talk to you a lot about that. And then there's also a weak force associated to radioactive decays. So rather than giving you kind of a Lagrangian for the standard model, which I could write down, let me give you instead a kind of picture of what type of interactions occur between the particles inside this standard model. And so there's different types of matter fields. There's things called leptons. These are generalizations of the electron, like a muon and a tau, as well as particles called neutrinos. And then there's, on this other side, other types of matter fields that feel the strong force, known as quarks. Those are the things that are inside a proton. And these are gauge theories. So we're talking about the electromagnetic weak and strong forces here. These are gauge theories with gauge bosons, the photon for electromagnetic, W and Z for the weak force, and gluons for the strong force. Okay, and so the leptons, for example, interact weakly and electromagnetically, but not strong. As you can see, the strong part of the diagram is in some sense the simplest because it's just the interactions between these quarks and gluons, and that's going to be much of my talk. I've tried to indicate here where things can self-interact, so the gluons can interact with themselves. It's what's known as a non-abelian gauge theory. The weak bosons can also interact with themselves, but not the photon. And finally, we have this player called the Higgs, and he can interact with everybody, he or she, can interact with everybody that's a quark or a lepton or a massive particle. So the W, the Z, and the leptons and quarks are massive particles. The photon and the gluons are not. And so we have those interactions, and it can self-interact as well. And this is going to play a role later in my talk, so let me just emphasize that we know in the standard model how it couples. A prediction of the theory is that the way that the Higgs should couple to these particles is proportional to their masses. So it likes to talk to things that are heavy. And that'll play a role later on. Oh. Yeah, just because we have both weak interactions, and I could have drawn two lines. This is just the one line like this and one line like that. Yeah, please do interrupt with questions. So let's look at the masses of the particles in the Standard Model. So just to kind of put in a scale to this plot, think of the mass of a proton as this dashed line here. So we have particles that are lighter than the mass of the proton. This is a log scale, so 10 to the minus 3 times lighter is the electron. And we have particles that are much heavier than the electron. Up at the top, we have the Higgs boson, something known as the top quark. And those things are as heavy as the gold nucleus, okay? So hundreds of times heavier than the proton. And so the Higgs, as I said, likes to couple to heavy things. So how are we going to produce a Higgs boson? It's very hard to produce a Higgs boson. Why is that? Because it's hard to produce things that have a lot of mass. If we collide together protons, inside those protons, some of the time, we can force the gluons inside those protons to fuse into top quarks, which are very heavy. So it's a quantum fluctuation of the gluons into this virtual top quark loop. The Higgs likes to couple to the top quarks, and that's actually the way that we produce most of the Higgs bosons at the LHC, is by this quantum process. The Higgs lives for 10 to the minus 22 seconds. It's barely there, and it quickly decays to other things. So it likes to couple to massive things. So for example, it could decay to 2 of these W bosons, which then subsequently decay to other particles. So really what we're doing when we search for the Higgs is we're looking for these final state particles and trying to reconstruct this virtual particle which was there for a very short time. Yeah, these are the gluons. Yeah, these are the gluons. This is a top quark loop. Higgs boson here, W bosons, and then electron, neutrino, sorry. Yeah, so these would be protons here. I'll draw it many more times coming up, but these would be protons, and this would be a gluon that's inside that proton. Okay, so as I already said, the Standard Model is a gauge theory. It's built on the principles of quantum field theory, which combines Lorentz invariance and quantum mechanics into a consistent framework. And let me just give you one example using the strong force. So the strong force is what's known as an SU3 gauge theory, built on the SU3 group. And its players are the gluons as well as the quarks. So we have matter fields, which are these quarks, different cases, up, down, strange. That's this index I. They're charged under this group. This is this index alpha. They live in a triplet representation. So that's the Lagrangian, which you can think of as equivalent to some Hamiltonian, if you like that language. And then we have a field strength tensor for the gluons in the theory. And it's a non-abelian field strength, so it includes for this interaction here, which causes interactions between the gluons, so they don't just interact with the matter fields like they would in quantum electrodynamics. We also have self-interactions of the gauge bosons. Okay, so that's a gauge theory, very simple. On one line, I can write down the theory for this. And the kind of phenomena that come out of that theory are quite remarkably diverse. So even though it's very simple, there's phenomena that come out, emerge from that Lagrangian that are very diverse. And there's just 2 different types of emergent phenomena that are actually important for my talk. So usually as a particle physicist, you don't really think about emergent phenomena, but I do. Okay, so there's protons, and this is a strongly interacting bound state of the quarks and the gluons, as I already said. So here in this picture, we have 2 ups and a down, as well as gluons. And that's an emergent phenomenon. It's not apparent directly from the Lagrangian. There's another so this one's well known. There's another less well-known phenomena that's important for my talk, and that is the physics of what are called jets. So if I have a quark, and it's very energetic, and I'm firing it along in some collider, it likes to radiate. So it has interactions with the gluons. Whether it's a quark or a gluon, it likes to radiate. And that radiation is collimated. So when the quark or the gluon radiates, the radiation that it produces keeps traveling in the direction that it was going. And so the way that a quark or a gluon is actually observed in a collider is by these things that are called jets. They're collimated sprays of radiation. Eventually, they hadronize into these hadrons, but they do so all in a collimated way, and they end up in a spot in the detector. Okay, and so that's how we really see that we formed a quark or a gluon in some collision. So these are two phenomena that we'll talk more and more about. And there's one other thing about the strong force that I have to mention, and that is that although it's very strong, so here's the value of the coupling on the y-axis here, it's also a function of energy. So depending on what energy you're probing, because of quantum fluctuations related to diagrams like this, the strong force actually changes its strength. And so at long distance, where you have these protons at small energies, the coupling is very strong, and that's the name strong force that it binds together into these protons. But at high energies, it becomes very weak, and it actually goes to zero asymptotically. That's asymptotic freedom. And that's the phenomena where this phenomenology of these jets comes in this region where the coupling is small. So we have these two different kind of emergent phenomena in different places in the parameter space. So this is a coupling as a function of the energy that you're probing. Okay. And this is something that you can predict. This behavior that you see in this line is something that you can calculate in this theory. And so you see on this plot that kind of calculation compared to experimental data verifying that this theory works. And what is this coupling constant alpha? Well, if we go back to the slide previously, there was this coupling constant g that was the parameter in my Lagrangian, and this alpha is simply g squared over 4 pi. Okay, so that gives some idea of what kind of where we start. What is one of these quantum field theories? Let's come back to colliders. So I already said that we want a lot of energy. Let me emphasize that even more. The reason that we want a lot of energy is because we need to produce these heavy particles. And we can convert energy into mass with m equals e over c squared. So we want to get as far out on this axis as we can. We also want to have a very high collision rate, which is this axis. And that's because these things that we're trying to probe are extremely rare. So for example, at the LHC, Large Hadron Collider, if we want to produce a Higgs boson, we collide together these protons, but only 1 out of every 10 to the 10 times that we collide those protons do we produce a Higgs boson. So it's an extremely rare thing. Okay, so we have to collide a lot of protons, as many as we can, in order to get a Higgs boson. And that's why when we build these colliders, we keep trying to move out in this direction. So I've shown here on the plot lots of different past colliders and the type of particles that were discovered at those colliders, including the Higgs boson discovered in run 1 of the LHC. And we're now currently in this stage of run 2 of the LHC where we hope to discover something else that's new. Okay? Yeah, it's just to guide the eye. Yeah. We want to move along this line. So the LHC is a 27-kilometer long tunnel, collides together these protons, and the type of collision rates that we're talking about here are 600 million collisions per second. Okay, so a huge number of collisions, of which you look at the most interesting ones and analyze them. Okay, so let's have a little movie about one of these collisions. So here's going to be the beam of the LHC. Here's a proton with the quarks rattling around inside it, going down the beam of the LHC. Now it's going into the detector and colliding with another proton. We zoom in on it. Maybe we produce a Higgs boson. We got lucky. It doesn't last that long. It decays to something else, to Z particles, which subsequently decay. And we get this spray of radiation associated to these jets, as well as perhaps some leptons that travel out. We have this huge detector, very, very large, that has all this has both tracking and energy information, and can detect these final state particles. So that was an animation, but here's a real picture of a collision. So you're seeing here the CMS detector, one of the detectors at the LHC. The two that will be important for my talk are CMS and Atlas, but there's also 2 other experiments on that ring. And in this collision, you're seeing the collision of the protons, and you're seeing the production here of 2 identified photons, these green bars. The bars are showing you the detector systems and what's observed. And then you're also seeing these sprays of radiation that are accompanying the collision. So the protons are coming in here, along this direction. Yeah, that's right. So some of the things are charged. There's a very high magnetic field here to do with particle ID. And so you have both tracking information of those charged tracks, as well as energy information, energy depositions.
These are happening hundreds of millions of times a second.
Yeah.
Are you getting many, many collisions all on top of each other?
You are getting many collisions on top of each other, the question is, what are the interesting collisions? And even on the interesting collisions, you're getting collisions on top of each other, and this is something known as pileup. And it's, as the luminosity is increased on the LHC, it's become more and more of a problem. So you can think of 20 kind of pileups a second, or per interesting collision, going up to 50. So this is something that experimentally you have to deal with, and they do have methods of dealing with it. Yeah. Yeah, it's just showing you different detector systems. So. So in this particular collision, the thing that really is important to me is the photons, but it comes in accompaniment with these extra sprays of radiation, and I'll talk much more about these plots and dissect them for you coming up next. Yeah. Yeah, I'll talk about it. No, I don't. Yeah, I mean strong radiation, really. Okay, but we'll come to what the theoretical ingredients in that radiation is in a minute. So these are the type of thing that led to the Higgs discovery. And I'm showing you here 3 different channels, the Z channel, the W channel, and the photon channel. And let me actually show it to you as a movie, because this is a statistical experiment where there's large backgrounds and you have to accumulate data. So most of what you're seeing here is the background. The red is the background. And you're accumulating data, and then you start to see a little bit of an excess above the data. In particular, right here, you can see that there's an excess growing that's above the background, and that's the Higgs boson. So this is 3 different channels, and it's particularly clear in this ZZ channel. In this WW channel, you also have an excess above the blue background, but you need to know that background very well if you want to identify a Higgs boson in the WW channel. And in this photon channel, you have a huge background, but it's a very monotonic background with no features. And this little bump here, this little bump is the observed Higgs. And all 3 of these channels agree on the Higgs mass, and that's what goes in. These are what kind of plots that go into the Higgs discovery. So that this is actually with more data than the Higgs discovery. And of course, the Higgs discovery led also to a Nobel Prize in 2013. In order to sort of talk about what happened since the discovery, I can quote to you the latest result that they have for the Higgs mass. And so the Higgs mass is now something that's known extremely precisely. It's 125 times the mass of the proton with very small uncertainties, both statistical and systematic. Okay, so that's the type of physics that I'm interested in. And how are we going to theoretically describe such a complicated system? So here's a cartoon that I'm going to use throughout my talk for these collisions. So we have our protons, we collide them, but what we actually take out of to actually collide are not the protons themselves, although those are colliding, but we want a parton, which is a gluon, for example, inside the proton to collide and produce our Higgs boson. And that's happening in this little magenta circle. And then out of that comes these jets, which are these blue things, as well as, for example, some electrons or muons, which are these dark blue. So time in this plot is going this way, and we make the collision. There's some place where the collision occurs, and then there's some final state that we observe. So let's go through this more slowly. So here's the kind of diagram that I had before with the gluons. These gluons are coming out of the protons. We're taking them out of the protons. There's a short distance process that occurs in this magenta window, and that's this production of the Higgs boson and then its subsequent decay. Okay, and that's a very short distance process, and that's why we want a very energetic collider. And then there's the physics of all the other things in this picture. There's these jets. So to answer your question about what kind of radiation is in this jet, maybe it started out as a quark, but then subsequently it starts to radiate, and I said that the radiation likes to be collimated in the same direction that the quark was traveling. And so here's a radiation of a gluon, which subsequently radiates into more gluons, et cetera. And eventually, long down the way, these things form into these bound states like the proton. And that's actually what you see when you look at the energy depositions in the collider. But this is how you see that fundamental quark that was originally produced. Okay. We also have jets that are produced prior to the hard collision. That's these green things in the figure. So there's jets in the final state, jets perhaps from the initial state. And then everything here carries color charge, all these quarks and gluons. So they can all talk to each other. And I've shown here in this figure them talking to what I call soft gluon radiation, which is these little ticks, just by way of reminding you that everything here has color charge and can communicate. Okay? So that seems at least like a picture for what type of thing is going on in these collisions. The L's are like a muon pair. This could be a mu minus and a mu plus, or it could be an electron and a positron. Okay, so actually that picture that I showed you had some assumptions built into it. But what leads to it is this concept of factorization, and that's what I want to turn to now. So factorization says I can take this process of this collision and I can actually describe it in pieces. I don't have to describe it as a whole. I can actually describe the individual parts and then put the parts together. And if you want to think about what really the underlying idea is, you can think, well, I want to calculate the probability that if I make a proton collision, I produce a Higgs boson. And I'm going to try to calculate that with conditional probabilities, okay? And simply multiply them together and sum over C. But really the hard part here is identifying what is this C, right? How am I breaking up my probability into pieces? And this analogy is, of course, not perfect. And in fact, the things that I'm multiplying together are not really probabilities. So the interpretation is not precisely this. But this gives the idea of what I'm doing when I try to describe the probability as a product of pieces. Okay, so I'll tell you what factorization is, and then later we'll see why it emerges. So what does factorization predict? If I tell you that this process factorizes, what does it say? It says that I can calculate those probabilities as a product of pieces. I have what are called parton distribution functions. So these are the functions in my talk. Parton distribution functions, which describe how I take that gluon outside of a proton. I have what are called hard functions. These are some short distance functions that describe how the Higgs boson was produced and how it subsequently decays. I have the production of these, I have the jets and how they evolve. So I have what are called jet functions, and so there's some initial state variety of that. And then I have also something called a soft function that describes how all this soft radiation in the event that can couple to all the different particles, how does that come in? And these things are combined in some manner that I've indicated by this tensor symbol, which could be integrals over different momenta. It could be sums over charges. And I'll give you some explicit examples of that later on. So that's what factorization is. So let's simplify that. That's rather complicated. You can simplify it in one way by saying I don't really care too much about the final state as long as I know I had a Higgs boson. So let me sum over all the possible jets in the final state. And if I do that kind of thing, probabilities add up to 1. And I vastly simplify the formula. All that dependence on the jets has gone away. The dependence on the soft function also went away. And I reduced the formula to simply these two pieces, the initial state protons and these things that I called hard functions. It's a different hard function than the previous slide, but this is a much simpler formula. And in fact, in this case, if I'm summing over all the final states, I can actually show you the full formula. Okay, so this is a full factorization theorem. I'm not hiding any of the details. So let me describe it to you. So we have these parton distribution functions. They depend on a variable, Ca or Cb, which is actually a momentum. And that's the piece of information that is exchanged between these protons and these gluons inside the proton and the production of our Higgs. Okay, so it needs to know the incoming momentum of those gluons. And these functions tell us the distribution or the probability of getting from a proton finding a gluon with a certain momentum. And then there's this hard function that one can calculate, and this function then has dependence on the Higgs mass, among other things. And that is giving you these probabilities in this case. And essentially, in this, there's another thing that shows up, which is this mu. And what's happened is I've taken QCD, which was both strongly interacting but getting weaker at higher energies, and I've divided up the physics, if you like, into the weak interaction part, which is this magenta object above the scale mu at higher energies, and then the strong interaction part related to the binding inside the proton inside these functions here. So there's kind of a dividing line, and this is actually a rigorous field theoretic dividing line. It's a cutoff parameter in the field theory that makes this distinction between these objects. So all these things have well-defined field theoretic definitions in this factorization theorem here. Yeah, y is actually an angle, or what's called a rapidity, but it's related to an angle, and it's simply in this an integration variable. And ECM is the center of mass energy. So at the LHC run 2, that would be the 13 TeV that they're colliding the protons together with. Okay, so those are the type of formulas that we want to use to make predictions. And yeah.
You sum of a final state.
Right.
What is the variable?
How do I know it's a Higgs?
Yeah.
Yeah. So I didn't sum over the leptonic variables. I only summed over the jets. So I could look, for example, at this case of the ZZ, just to give one example, and I could have the Z bosons decay to leptons, say 2 mu pairs and another 2 mu pairs. And then everything that came from the Higgs decay was not strongly interacting, okay? And so I could reconstruct the Higgs boson purely from leptons, and then I just sum over the jets. That's the simplest example. So let me give you a little timeline of how you prove a formula like that, of what kind of ingredients went into it. So there was early work by Bloch and Nordstick, which taught us how to think about states in the quantum field theory and what are reasonable observables. There was important work by Landau, who taught us how to figure out what are the right degrees of freedom to even have this conversation in terms of. And then there were things called soft theorems, work by Lowe as well as by Weinberg, that taught us about how the soft radiation that came into my picture, how it couples to these degrees of freedom. Things. But then this all kind of came together and culminated in the 80s with very important work by Cohen, Soper, and Sturman. So they were the ones that gave the first rigorous proof of this formula that I showed you for Higgs production. Okay, that kind of thing was very important, obviously, for the collider physics program, but these proofs are rather difficult, and not a lot of the community is able to deal with them. So in the 2000s, in work that I did with collaborators, we took this idea of making these proofs and turned it into instead an idea of constructing an effective field theory that would be able to give you the same tools, all the tools to make these types of proofs. And that theory is what's known as the soft collinear effective theory. And the way I'd like you to think about it is as an emergent effective field theory. So we had QCD. It was not obvious that these jets were there in QCD, but in this effective theory, these jets are kind of going to become the degrees of freedom of the effective theory, or close, not precisely, but they're going to be very apparent in the construction of the effective theory right from the get-go. So we're going to construct an emergent effective field theory from our full QCD. Okay, so what is the simplifying idea that allows me to do that? And the simplifying idea is that there's different scales in this problem, different energy scales. There's, for example, the very low energy scale associated to the binding of the proton, and the very high energy scale associated to the Higgs mass. And I'm going to separate those scales, and I'm going to make expansions. I'm going to expand in the ratios of those scales. There's also intermediate scales associated to the formation of the jets or the soft dynamics, and I'm going to be expanding in all those ratios. And effectively what I'm doing is I'm describing by the different parts of this diagram, I'm describing those different parts as different quantum fields in the quantum field theory. Okay, that's technically exactly what I'm doing. And then I'm trying to figure out exactly how those fields all interact with each other and construct an effective field theory of that. So I'm putting in this picture that there's going to be collisions, that there's going to be certain directions that are important associated with the jets, associated with the initial collision, that there's going to be this soft radiation which has different properties than maybe the collinear radiation that's inside these jets and collimated. These things are part of the construction of this emergent effective field theory. And it's not a one-dimensional picture anymore. I can't just describe it by energy. And you can see that in this picture because I have to talk, if I said that there's a scale associated to the jets, well, still this jet and this jet are different objects in this effective field theory. And that's because the direction is also important. So it's actually a multidimensional, or at least a two-dimensional description, where I have degrees of freedom that live at different places in momentum space and have to figure out how they communicate with each other. So this is my cartoon of that. These are two collinear degrees of freedom, and here are some soft degrees of freedom. There's going to be some dividing lines between these degrees of freedom, and then these are going to be described by quantum fields, and I have to construct an effective Lagrangian for that. So the dominant contributions to these types of processes come from isolated regions of momentum space. And the boundaries here, even though I drew them kind of as sharp lines, they're not actually sharp because you have to preserve things like gauge symmetry and Lorentz invariance to some extent. So there's more complicated technical ways of drawing these boundaries related to distributions and subtractions and things like that. But I'm not going to get into it. You can ask me afterwards. So I take this quantum field theory, I write down fields. These fields are now labeled by a direction, NB. That's the direction of the radiation of the proton incoming, NA, N3 here for this jet 3. As well as I have some soft fields to describe this very low energy radiation. So these are the actors now. And what are the kind of things that I do to put that field theory together? Well, one very nice thing about this field theory is that I can construct it. It's a constructive effective field theory. And that is, I can take QCD and this effective theory that I'll denote as SCT for soft collinear effective theory, they have to agree at long distances on all the infrared physics, all the low energy physics. The short distance physics they don't agree on, but that physics is encoded in the effective theory in some Wilson coefficients. And since I can actually do calculations to construct this effective theory, because the short distance physics on which they don't agree is exactly where the coupling is perturbative. So I can do perturbative calculations as a way of constructing this effective theory. There's a power counting in this theory. I have to know exactly how important everything is. And that's in some sense a very, very important ingredient in this effective theory, particularly when you're introducing these cutoffs, that you don't mess up those expansions that you're trying to do. So that's an important ingredient. There's also emergent symmetries. So in the original theory, we had a gauge symmetry. And there's actually here, now in this effective theory, gauge symmetry in the different sectors. We had these gluons, but now we have gluons in direction N1, gluons in direction N2. And there's a gauge symmetry within those different sectors that we can exploit, as well as other generalizations of Lorentz invariance that we can exploit. And the kind of, after you make this construction, what you find is that the new objects that are appearing are what I call these building blocks. And they're kind of quark fields in a given direction, dressed by a Wilson line, as well as an analog for gluons, where you have some dressing by a Wilson line. And in a very real sense, these are the fields that are producing a quark jet or producing a gluon jet. Okay. So let's see, going to our picture, how that works. Scale by scale, I start at the top. I integrate out this hard scale. And what happens is I shrink this blob here to a point. I get some effective operators, and I get some effective coefficients that encode the physics of that short distance that I'm integrating out, removing from the theory. I have to figure out what kind of operators I have, and those operators are built out of those building blocks. So for example, I had two gluons come in, and a pair of quarks and a gluon go out, then the type of operator that I would have would be this one that I've written down.
You're always below the strong scale.
Yeah, the strong scale is down. The scale where the coupling really becomes strong is down here. I'm always above it. Yeah, that's why I can make this construction perturbatively, for example. When I write down these operators, I haven't done perturbation theory. Perturbation theory would come in telling you what this coefficient is. It's a series expansion in the coupling. Here I've actually only made an expansion in powers, in ratios of these scales. And that's important. Yeah. Yeah. That's right. Yeah. Yeah. Yeah, it is the rearrangement of the color indices is done by these soft particles. Yeah, absolutely. Yeah. Yeah. And you can see when you go through the math, I didn't write any of these color indices here, that you can see how those indices get rearranged. Finally, the soft particles. What the soft particles actually know about are not very many of the properties of the jets. They just know about the bulk properties of the jets. So they know whether it was a quark or a gluon. how it was charged, so an overall charge of the jet, as well as the direction it's traveling, and that's it. So these soft particles can actually be described by another set of Wilson lines, soft Wilson lines. And that is what you derive when you do these expansions, and that goes also back to the work of Francis Lowe. Okay, so this is how you get to a factorization theorem. You have a hard scattering operator describing the collision, which is actually just a product of things, which I've carefully color-coded here to match with my figure. It's just a product of things that live in different sectors of the field theory. And if you construct the Lagrangian of this effective field theory, it turns out that the sectors themselves are decoupled. Okay, at leading order in your expansion, they're decoupled. They can couple back together at higher orders, but at leading order, there's just a direct sum. Okay, and so you have a product operator, direct sum Lagrangian, and that leads to factorization. If you square this and you try to calculate cross-sections, probabilities, then you get these factorization theorems. And exactly the nature of these tensor symbols, that comes out in the details of the math that I'm not going over. Although I will give you some more examples. So why are they universal? Yep.
Factorization seems to suggest that these different scales are independent. But
Yeah.
I think that as you integrate out one scale, it'll renormalize the next scale.
That's right. So, so all these functions depend on these dividing lines, right? And you can control that dependence in this formula. There's also these tensor symbols, which are sort of how do degrees of freedom in this sector talk to degrees of freedom in that sector. And that's kind of the most important thing in this formula, which is how can that communication take place? And it's related to these expansions because degrees of freedom can only communicate if they have a momentum that's commensurate. So if there's a hierarchy between two momenta, then you won't have communication that's important. But if they share a momentum that's of the same size, like this guy and this guy share the same size of momentum in this direction, then they can communicate. And so that's going into these tensor symbols. Okay, these hard functions describe the short distance process. They're independent of kind of the details of the measurements that you make on the final state jets. So that makes them universal. These jet functions, they really only care about the jet dynamics. They don't care about the underlying hard process that produced the jet. They do depend on some of the things that you do with the jets subsequently, but they also have a universality to them. These soft radiations, I already said, they only really depend on the bulk properties of the jet, so they have a universality. And then finally, these initial state parton distribution functions really just depend on properties of the proton, which can be calculated independently of even doing a hard scattering process, so they also have universality. This kind of factorization underlies all the predictions that we make for collisions at the LHC, whether we make them by directly calculating with these factorization theorems or using more sophisticated or more complicated Monte Carlo programs, which usually are lower precision but can calculate any observable you want. They're all based on this idea of factorization. There's an important thing that comes out of this, which is this separation between the strong dynamics and the weak dynamics. And that's particularly important here because some of the functions here can't be calculated in perturbation theory, like these ones associated to the proton. And by having this factorization theorem, we know which ones those are. We know some things should be expandable in the coupling, other things can't be. There's results related to resummation of logarithms, which is related to your question of these scales, these dividing lines. We can actually exploit those dividing lines to sum up infinite series of terms in the quantum field theory, and I'll show you an example of that later on. And finally, something that is kind of a key motivation for giving the talk this way. I presented it to you like we have this formula that we've proven, but the question is, how many cases are such that we've actually proven this type of formula? And it turns out that if you think about the space of interesting observables, so these are kind of the space, this is the space of measurements you'd like to make at the LHC. The kind of corner in which we've actually rigorously shown that these kind of factorization theorems are true is not very large. And furthermore, we're not even sure exactly how the dividing line would be between the things that factorize and the things that don't factorize. there are some theoretical examples that you can construct that are known not to factorize. But interestingly, we actually can still make predictions for things there. We don't have a rigorous theorem. And sometimes those things just agree with the data. So the data here is telling us that factorization is true for a broader set of examples than we can prove, for example, with the methods I was outlining. But there's also examples of cases where if you apply factorization, it doesn't work. And there's non-factorizable effects that are important. And so that also the data is teaching us about. And part of the motivation in going forward in this field is actually trying to move this line out. And using these effective field theory techniques is one way of doing that. I'll come to also some ideas related to that at the end of my talk, and trying to figure out what exactly theoretically determines that line is a motivation.
These non-factorizable examples are also in the context of collider.
They are.
What are the examples?
Yeah, so you can, for example, take proton-proton to two jets. In each of those jets, you can measure a single hadron, so a fragmentation process. You measure the perpendicular momentum of those hadrons, and you sum the perpendicular momentum together. They're going to be back-to-back, so if they have some momentum that's perpendicular to the beam, when you sum it together, it's going to get smaller. So essentially what you're doing by summing it together is you're measuring the transverse momentum of the particles in the collision. And it's known for that particular observable that there's not factorization. Essentially in that case, because you have trouble constructing the hard scattering operators, you can't do so uniquely.
Areas of this region you draw give us an approximate scale.
No. Yeah, I don't know where this line is at all. It could be over here. It could be over here. I don't know. Yeah. I mean, you can, yeah. Anyway, you can sort of bias it a little bit by the experiments, and that's why I drew it in the middle. But.
Can you clarify the connection or lack thereof between whether it's factorizable or not and whether there's indications of new physics? How do you
Yeah, so you definitely want to rely on factorizable things, right, to look for new physics. And luckily, this Higgs, and luckily things related to Higgs couplings fall in this square here.
New physics, but it was on the right-hand side of your diagram?
Then I'll talk a little bit more about it, because you can, even though you can't use the quantum field theory to calculate these things, you can still model them. And that people do, and I'll show you some examples. All right. So how could factorization fail? The choice of the measurement, as I just gave in this example, could cause it to fail, and it could be related to the matching failing. You could also encounter divergent integrals, and there's other examples of this type where you try to separate these degrees of freedom, but you end up with things that aren't well defined. And there are examples of that type where basically you don't precisely know how to define the functions that are showing up in the factorization theorem. All these things you would see in the effective field theory. One thing that's more dangerous from this effective field theory point of view is whether you've got all the degrees of freedom, the right degrees of freedom. You're basically relying on the past work in order to identify the right degrees of freedom. And I'll say more about that at the end of my talk. So let's go through a couple of examples of factorization. So one is, instead of colliding protons, I could collide electrons. Here the relevant variables are the energy and something that's called the jet resolution, which is basically telling me how fat this spray of radiation is. This is just giving you an idea of how these factorization theorems would actually work. I take this observable, I can write it out in QCD as a square of matrix elements integrated over phase space. I expand using my effective field theory. I group terms into the conveniently color-coded hard, soft, and jet matrix elements. And then I do some algebra on it and carry through everything carefully, and that leads to these factorization theorems. So that's where these objects that I was talking about actually emerge as quantum field theory matrix elements. And this here is kind of why I said this was a jet field, because this quark field here is really responsible for a jet. And this jet function is just the square matrix element of that type of field. There can also be non-perturbative physics that not only arises in these parton distributions, even in these E plus E minus collisions, the soft radiation can bring in some non-perturbative physics that can't be calculated with a coupling expansion. So we can think about now making this these predictions. Here's a prediction if I just work at fixed order in the coupling. I don't really need that factorization theorem to do that. I could just calculate with QCD. And you can see that the expansion is not converging very well. If we sum up the logarithms of this variable, this resolution parameter tau, then things start to converge much better. Essentially, this means that the logarithms are large and that you need to sum them up. And so here, as shown in red, is sort of the highest order prediction. This is work in part by my group. And you can see by the plots here how things are converging, as well as an estimate of higher order uncertainties given by the width of these bands. If you include the non-perturbative corrections and you're careful about dividing up the perturbative and non-perturbative physics, then the convergence actually even gets better, and we get to predictions that are at the percent level, shown by this very thin band here. That can be compared to data. So here's a comparison of that to earlier colliders. These are earlier colliders in the LHC. And this is a 2-parameter fit that we've done to 2 parameters that come in. And it's not just the fit to the data shown on this plot, but there's many other plots of the same type that are for different center of mass energies. So we have hundreds of bins of data. We make a 2-parameter fit, get a chi-squared per degree of freedom of 0.9. Theory is working very well. And out of it, what we get are a measurement of the strong coupling. So this is a percent level measurement with control over all the uncertainties. The dominant uncertainty is actually coming from the theory side. So these estimates of how thick these bands are important for the uncertainties. And we get also some estimate of the second parameter is related to this soft non-perturbative physics. It turns out that there's just one parameter, and we can also measure that. So this is showing you the theory in action, making predictions, comparing to data, and working. Yeah. To 2 jets. Yeah.
So what is the problem? So theoretically, this is what, but
Yeah. Yeah.
way to find it.
That's right. So here, so that's related to this resolution parameter. Here they're being very inclusive over the jets in this E plus E minus collision. There's no jet algorithm in this case. Yeah, it is, this observable. But this would not be. So if I were to do PP to a jet plus anything, that also is something where now I'm showing it on a log scale and I'm showing predictions at a lower order from a different group, not ours. And they also have to account for the parton distribution functions, which is mainly what these groups are about, these proton matrix elements. But you can see again that you have fair agreement for different jet energy scales, and here transverse momentum, but that's jet energy, or different angles as shown by these different curves. The agreement here is not at the percent level, more like the 10% level. So this is factorization working also at the LHC for jets. Now I can come back to this formula that I told you about and actually make something interesting out of it, because I can use it to talk about how the Standard Model coupled to all the particles. And so I can attach to this production, the decay, and make a measurement of the Standard Model couplings. Okay, this couplings to all these particles, and ask, is the Higgs behaving like it would be in the Standard Model? And this plot from Atlas and CMS combining their data shows that very nicely, because the prediction from the theory was it should couple proportional to mass. That's this blue line. And you see for the different particles, B quarks, taus, tau leptons, W bosons, Z bosons, top quarks, that things are indeed coupling to mass in the way that we would expect. Now to look for new physics, you're actually interested in making this plot in a different way, getting rid of this mass factor and looking for deviations of these couplings from the Standard Model. But at least as a way of verifying that the coupling to mass is true, this plot is very nice. So this thing that I mentioned to you long ago, that the Higgs couples proportional mass, is borne out by this analysis, and this really just depends on the factorization theorem that I showed you that can rigorously be derived. There's some details, which I'm a little short on time, so I'm going to skip over. There's some details related to making cuts on the data, and you can derive factorization theorems even in the presence of the cuts, and my group has worked on that, and you still get fair agreement with the data even when you make those cuts, and you have a more complicated factorization theorem than the one I showed you. In this particular example, there's a little fine footnote, which is that we've been careful about the first 3 bullets here, but we haven't really been fully careful about this last bullet, about the fact that there could be some additional modes that spoil the factorization. And this is related to these observables that I mentioned to you, where we know that factorization is spoiled. So we don't really know fully for this kind of these cuts on jets whether factorization is spoiled or not. We do know for other observables that it looks like it is spoiled. And this is an example of that. It's something called transverse thrust. But basically, the theoretical predictions take curves that look like this, and they move them over to curves that look like this blue dashed line once you add non-factorizable effects, which are generically here called underlying event, or I'll just call it UE. So if you add these UE effects, you model it. It's not coming directly from a quantum field theory prediction. You get these blue curves. And those blue curves are actually what agree with the experimental data, analogs of those blue curves. So the experimental data is telling you that there's things that are outside of factorization that are actually important. So what people do is they try to model it as best they can. But what would be actually nice is to have the quantum field theory description also of that. And in the last 1 minute or two, I'll tell you about some work that we have in progress in that direction. So I said that there was one thing that we left out of the effective theory, and that's something that's called a Glauber mode, after Roy Glauber, actually, although not directly related to his work, but indirectly. And this mode actually is the thing that can cause factorization violation in some of these cases. And so it's kind of the last ingredient that you would need to fully understand, we believe, to sort of map out this uncharted territory. And really what this mode does is it kind of acts like a potential between the energetic particles, or between the energetic particles that are collimated and the soft particles. It couples them back together. And that spoils factorization. If you couple them back together and it's a leading order effect, you spoil factorization. And with my collaborator, Ira Rothstein at Carnegie Mellon, we've worked out the effective field theory for those modes. So the dangerous type of interactions are actually not the ones involving most of the collision that I described to you, but actually related to these other guys that are called spectators that are present in the collision and just kind of go along for the ride. But if they can scatter again, then those can cause a violation of factorization because it can recouple your protons together, for example. And there's an effective field theory that we've derived for that. And what it turns out to do is it has interactions between two sectors, like these collinear and soft sectors, or three sectors, but not more than three. And then it's really described in terms of very particular operators. I've written down some expressions here. They're perhaps not obvious operators, as you can see, but you can derive this. And so our hope is to use this Lagrangian to describe factorization violation and be able to understand more of that picture. We're still in the very early stages where we're just working out the formalism, but that's the idea. So what kind of things have we done? We've checked matching between the full theory and the effective theory, both for tree-level diagrams as well as loop-level diagrams, making sure that all the infrared physics is correctly reproduced on both sides of the equation, and charting out how this effective theory works. This effective theory has certain singularities that you have to be very careful about when you're dividing up these degrees of freedom, and they show up in these loop diagrams. And so that's another thing you have to be careful about. You can try to reproduce known effects. You've got these regulators. Do you correctly reproduce an iconal scattering formula? Just forward scattering of two energetic particles, and you do. You can also look at other forward physics that people have derived in the past. Back in the 70s, something called the BFKL for Bolitsky, Fed, and Karev-Libetov was worked out, and this effective theory derives that as well. So you're reproducing a lot of known physics. Actually, our derivation of this BFKL equation, which is textbook material, is very, very simple. So that's kind of a nice thing. The effective theory should make things simpler, and it does. And finally, you could ask about the impact of these exchanges on hard scattering and factorization violation. And it really is these diagrams that I told you about between the kind of spectators in the interaction, not between the active guys that are participating in the hard collision. So if an active guy that's participating in the hard collision were to interact with a spectator, those aren't dangerous. It's really these guys with the spectators that are dangerous. So where is this going? It's going towards charting out more of this figure that I drew. This gives you some more fine detail of that. Okay, so I'm out of time. Let me conclude. So we have the discovery of the Higgs boson. We have our understanding of the factorization that goes into making these predictions. And in some cases, we can make very accurate predictions compared to data. And I'll give you two examples, the strong coupling and the measurement of the Higgs couplings. And we have progress towards understanding more of the physics of that Venn diagram. Thanks.